Good afternoon. So we now see the theorems based on circles. This is a part of the chapter that is symmetry. And because circle has a symmetry across all the diameters, so this is almost like a universal symmetry. That's why circle is also a part of the chapter called as symmetry. So apart from the circle, the other part of symmetry we'll see in the second video. We'll only focus on circle in this video right now. Let's see. There are certain theorems. The first theorem is perpendicular bisector of a chord will pass through the center. So this is the circle and O is the center. In this circle, I have drawn a chord. This is called AB. You know what is a chord? A chord that is a line that passes through two different points on the circle. So this is one point, this second point. It passes through them. Chord can also be a diameter, that will be the longest chord. This is a chord. And the midpoint, we are talking about the perpendicular bisector. So it is also a perpendicular line and it is a bisector line. Bisector is the line that bisects the given chord. So to bisect, it has to pass through the center of it, the midpoint of it. So I'll mark the midpoint of this. This is the midpoint. Now on this midpoint, if I draw a perpendicular passing like this, then this perpendicular will pass through the center. That is what the theorem says. This is the perpendicular and it is passing through the midpoint, so it is bisector as well. So this is perpendicular as well as bisector. So the perpendicular bisector of a chord will pass through the center. The opposite, the vice versa, or the converse of this is also true. That if I from the center of the circle, if I draw a perpendicular on any chord, then that perpendicular will bisect the chord into two equal parts. So we can use these theorems to solve some problems. The next one, the tangent drawn to a circle from an external point, from a point that is outside the circle, same point and outside the circle, are equal in length. First of all, we got to understand that in a circle, if you consider this point which is inside the circle, I am not showing the point, but imagine any point inside the circle, here or here or here, inside the circle. So if you see this point, any point inside the circle, if a line is passing through these points, it will cut the circle, it will not touch the circle. Touching is possible only if it is like this, which means that a single point of contact. So for a point inside the circle, you cannot draw any tangent, because tangent is only possible if the point is on the circle. If you take this point or this point or this point, which is on the periphery of the circle, circumference of the circle, there one tangent is possible. Exactly one tangent. But if you take a point outside the circle, then from here one tangent like this and one tangent like this, two tangents are possible. And that is what the theorem is talking about. So this is the point P from where one tangent is drawn, this is the radius. Same point P, the second tangent is drawn, this is the radius. This point OP is the distance of this point P from the center. Our theorem is saying that the two tangents drawn to a circle from the same point outside the circle. Outside the circle, same point, and we are drawing two tangents, PA and PP. Then their lengths are equal. So PA must be equal to PB, is what this theorem is showing. PA is equal to PB. Is it really equal? We can very easily check that. We can check this triangle AOP and BOP. This line AO and this line BO will be equal because they are radii of the same circle. Line OP is common in both the triangles. And this angle is 90 degree, this angle is 90 degree, because the radius and the tangent at the point of contact are perpendicular to each other. So this is 90, this is 90. So if this is 90 degree angle, this is hypotenuse and this is one side. So as per the RHS theorem, both the triangles are equal, and if both the triangles are equal, then their corresponding parts will also be equal. So this side is equal to this side. AP is equal to BP or PA is equal to PP. And that's how we say that tangents which are drawn from an external point, from a point outside the circle, are equal in length. Two tangents will be equal in length. Next, the angle in a semicircle is a right angle. The CBSE uses a slightly complicated word. It says that the angle inscribed in a semicircle is a right angle. What is that? See this circle. I draw a diameter. So this is a semicircle. This is a semicircle. Half, exact half of a circle. APB will be a 90-degree angle, right angle. AQB will also be a right angle. Why? Because the line. There is one more theorem that we will see, and that theorem is if there are two or more angles which are a part of, they are inscribed on the same arc or the same segment, then these two angles will be equal. These two angles are inscribed in the same arc, same segment. See this. And this is also in the same arc, same segment, AB. So these two will be equal in length, equal in angle measures. And this is 90 degree, this is 90 degree. Why? Because the angle inscribed in a semicircle or angle in a semicircle is a right angle. It is very easy to prove that if we have to, but then we'll just go on. The angle at the circle, the angle at the center of a circle is twice the angle at the circumference. Again, this is very easy to understand. Let's see this center. Angle at the circumference is APB and angle APB is x. If angle APB is x, then angle AOB will be equal to 2x. Why? Because the angle at the center of a circle is twice the angle at the circumference, provided both the angles are subtending the same segment, same arc AB. So if this is x, this is 2x. If this is 2x, this is x. If you know one of the two angles, the second angle can be easily found out. Next, this theorem can be used to prove this one. This one. This entire angle from here to here will be 180 degree. The angle at the center AOB will be 180 degree. If this is 180 degree, then angle at the circumference will be half of that, and the half of 180 degree is 90 degree. Imagine this AB is this arc as the arc which is subtending an angle of AOB at the center, and the same arc is subtending an angle of APB at the circumference. Then as per the next theorem that we saw just now, the theorem that we saw is the angle at the center is twice as compared to the angle at the circumference. So this angle we know is 180 degree. So this angle has to be 90 degree. There is no other choice. Any angle, any other angle here will be 90 degree. You have seen this. The angles in the same segment are equal. Here you see this. APB, AQB are the two different angles in the same segment. AB is the segment, minor segment. Therefore, these two angles are equal, x and x. Opposite angles of a cyclic quadrilaterals add up to 180 degree. Let's see the diagram. A circle, a quadrilateral, a cyclic quadrilateral. A quadrilateral is called a cyclic quadrilateral if all the vertices of that quadrilateral are on the circumference of the same circle. If you take any quadrilateral and if it is possible that all the vertices of that quadrilateral are lying on the same common circle, then that quadrilateral is called a cyclic quadrilateral. And if it is a cyclic quadrilateral, then opposite angles are supplementary. Their addition is 180 degree. A, B, C, D would have been the normal case. I am only taking these two angles. B and D are, because the quadrilaterals add up, total angular addition or sum of the angles is 360 degree in a quadrilateral. So we'll do first A and C. B and D are obviously proven. We'll talk about that later. This is the central angle. Now X will be equal to twice of C. Why? The angle at the center subtended by the same arc or the same segment. Yeah, this one. The angle subtended by the same segment at the center is twice the angle it subtends at the circumference. So X is equal to 2C. X is equal to 2C. And Y is equal to 2A. Same logic. But X plus Y is 360 degree. X plus Y is 360 degree. So 2C plus 2A is 360 degree. 2 common. A plus C or C plus A is 360 degree divided by 2. A plus C is 180 degree or C plus A is 180 degree. So the sum of opposite angles is 180 degree. If these two addition is 180 degree, the total sum would have been 360. So in दोनों का addition भी 180 of course. We don't have to worry about it. This is the theorem for cyclic quadrilateral. Alternate segment theorem. Just pay attention to this. What we have initially is we have a tangent. Right at the point of contact, I will draw the chord. Now after this, I should have done that. Right, this is the tangent, and this is the chord. In between them there is this angle. Now what I am saying is, now you join this point and this point anywhere. This point and this point join anywhere, any other point on the circle and make an angle. This angle will be equal to this angle. And this is called as alternate segment theorem. So this angle would be equal to this angle. First, let us just verify. What I have done is to verify. What have I done is, I use these two lines, red lines, and using these red lines, I am forming this angle. And I have purposefully not completely aligned these two lines with the actual lines because I wanted to show it like this. This is parallel, this is also parallel. So you can see the angles are equal. The angle is here. And the same red line, without any deformation between them, will come here and will mark the same angle here. Let's see this. See, the angle is equal. So these two angles and this angle and this angle must be equal. But we can prove it as well. How do we prove it? Alternate segment theorem. The point of contact. At the point of contact, we will draw any chord. So we draw this chord PB and it's making an angle of X. From here B to end point P, this segment is subtending an angle of PQB and that angle is called as Y. Does it have to be at Q? No, it can be anywhere. This point, this same angle could have been formed here as well. Join this. So the point Q could have been here, the point could have been here, anywhere. There is no restriction to that. This angle and this angle should be equal. To prove these two angles are equal, from point P, I have drawn a line which is passing through the center. So this is the diameter. AP is diameter. AP. If AP is diameter, very clearly, please note this. Then as per the tangent radius theorem, as per the tangent and radius theorem, this entire angle OP, and if this point was Q, let's say, or R, OPR, this entire angle would be 90 degree. This from here to here would be 90 degree because this is tangent, this is radius, they are perpendicular to each other. And this entire angle is 90 degree and this is x, this would be 90 minus x. So please see this, this is 90 minus x. If this is 90 minus x and this is 90, why is this 90? This is a diameter. So this is angle in a semicircle, and angle in a semicircle is a 90 degree angle, right angle. So this is 90 degree, this is 90 minus x. This has to be equal to x, there is no choice. Because otherwise the addition will not be equal to 180 degree. This P, A and B are, this is a triangle, APB or ABP, whatever that you call it, is a triangle, and the addition of all three angles must be equal to 180 degree. So this is 90 minus x, this is 90. So together they are 180 minus x. This must be equal to x. Only the x gets cancelled and answer is 180. So this angle will be x. If this angle is x, please note this. This angle is subtending an arc or subtending a segment PB. And the same arc is subtending an angle here as well. So the angles in the same segment must be equal angles. So x must be equal to y. See, this is the arc, this is segment, and this is x and y are the angles on the same segment. That's why these two angles must be equal. So x is equal to y. So this was x. So x is equal to y. And we have proven this now. So this is it. I remember there was one problem where in our class we were discussing that from a previous question paper, and we were discussing that particular problem, and we spent a lot of time to figure out. And that problem was based on a circle. We were using this. At that time we did not know this theorem, and we were not studied this, and it completely slipped out of my mind as well. So we were trying all possibilities, but we did not get a complete answer, and the complete answer would have been obtained by the alternate segment theorem. I hope this helps. Please do study. Solve the questions based on the exercises based on circle. They will be very simple, and if there is any doubt, you can always reach out to me. So the entire topic of circle finishes here. In the next video, I will do symmetry. Thank you.